Hello and welcome to my short video highlighting the following areas. I'll be highlighting sending and receiving messages on the client server, serialization and deserialization of 3 static objects and 2 dynamic objects, synchronization of the game world, and unit tests with the Google Test Harness. In the video, I will show the game running with multiple connected clients. Firstly, I want to go over the sending and receiving of messages from client and server. I'll start within the TCP socket test harness. For each TCP and UDP socket, we'll need an echo test. So we're creating an echo test within the test harness, and we're ensuring that the IP4 from string is echo TCP, and then that the client pointer operator is connect and with the socket address. We then have a string send string of hello world TCP. I've put the TCP just to ensure that it's highlighted and we can differentiate from the UDP within the terminal. And then we have an integer of write count, which is equal to client arrow operator of send, of the send method with the send string length. Now, if we go to the definition of send, you can see that the integer of byte count is equal to the send and the socket with the static cast. And then if that byte send count is lower than 0, which means there's no bytes within the socket to send, then we send back a TCP socket send error to show we clearly know where that error is coming from. The same with receive. If there's 0 bytes within the received socket, then we'll send back an error of receive, so we clearly know the error. Then if we go back into test harness, you can see here is the receive call, and then into UDP, which has a very similar setup, which I've changed the hello world to UDP to highlight that again. Then we have the write count, but this time it's send to and receive from. So if we go to the send to definition, it has a similar but not exact definition method of what to do if the byte sends count are sent to the socket and if they're lower than 0. However, we still have the error logs that are presented if they are lower or equal to 0. So now that I've showed you this, I'll quickly go over the results. So if I make network test the startup project, as you can see, the startup tests are already working, but to actually get the echo tests, we need to make a TCP connection port and a UDP connection port. So if I open up Gitbash, I'll first start with the TCP. You can see when we open the TCP port, it says it sent hello world TCP, which we highlighted, and received the message hello world TCP. Now, if we go back and do the UDP, you can see that if we scroll down, we have sent hello world UDP and received hello world UDP from the client to the server. So both messages have been received. Then also the non-blocking mode test, that's also sent hello world and received hello world. So this shows a message sent from the client to the server has been successfully received. For the serialization and deserialization of static and dynamic objects, I wanted to first go over the player object as it's a dynamic object. So firstly, in the player.cpp, I wanted to go over the write method for the serialization. Because it is a dynamic object and it will have interchangeable values, it needs to use a dirty state for the server to have access to these changeable values. So we have, firstly, a written state of 0, which is just the index and the enums, and all the enum lists of ECRS, player ID, pose, color, and health. So, for example, in the position, we're saying that if you're in the dirty state and you want the position, so from the enum list, then you write the x and y value of the velocity and location, and you can't pass the whole vector because it takes it in as 1 bit. So, but if you're not directly in the state or position, then it will return back false. So after you've written these x and y values for the velocity and location, we're then saying that the written state, so the index and the enum is now equal to the position. So all of these values that you've just set, that is now equal within the position enum. So, and like I just said, if it's not the case, if you're not in the dirty state or the position enum, then you return back false. This is the same for thrust, health, and then for the player ID. It's just a replication. So now if we go back into read, which is in player client, we can see the read function for the serialization is, firstly, it reads that if the state bit is equal to true, as you can see here, if it's equal to true, then you get the player ID. The player ID is then read using this method for the player ID, and then set the ID. And the read state will then be equal to that player ID. So the moment you write something, it's instantly reading something. So the moment you set the ID, the player ID, it is then read that ID and is setting that ID. So you can see this in the if state. I've shown you the client. I'll quickly go into player server, and this is where it handles if the deserialization. So if the player dies or collides with an NPC or bullets or anything, it will do do an instance of the network manager and unregistering this game object, deleting it from the world, and then it will update and get the position of the player, and using a human, it will just start the player movement update again. So if it's human controlled, it will just start again. If it's the AI, it will just stop because in between the functions in the player movement function, it starts again. In the NPC function, it doesn't start again. So with the handle collisions with player, you can see that the main player ID will equal so we're just defining each of these integers here, and then if the player ID is equal to 0, nothing happens, but else just take damage. If it's not equal to 0, then the player can take damage. If it's lower than 0, obviously the player's dead and it no longer can take damage anymore. Now I'll go over the static objects. So firstly, I'm just going to go over an example of one of the static objects and then show how I've replicated that for each one with the slight changes, especially within the pickup static object. So firstly, I'll go into tire.cpp. So you can see the written function in tire.cpp straight away has a written state of 0, and it returns at the bottom just a written state. So it first gets the game object location, writes the location, writes the get rotation, and writes the get color. So if we go to the corresponding tire client, we can see that in the read function, it gets the rotation, gets the location, reads the replicated location, reads the replicated rotation, and reads the color that has been set. So if we go into tire server, you can see there's nothing here. It's just an update. But this is the same for house, the house.cpp static object. However, where it differs is the pickup object. We have the same write and read methods, but in the pickup static object server, we have a handle dying and handle collision with player. This is because I wanted, when the pickup static object is collided with the player, I wanted a parameter to happen. So although this is not ideal, right now I've just got a function that changes the speed of all player dynamic objects in the scene. So although it doesn't only manage one object right now and all the instances of it, it's just to show a variable when the player collides with it. It is then using the handle dying, which is used in Bullet. I use that to delete the object away once the player has collided with the pickup. Quickly, I wanted to go over how the objects are registered. So in the client, .cpp, you can see that the game object registry instances for each game object, so that these game objects can be registered through the client. And if you go to these actual, the definition of this, it is within the game object registry.cpp, and this is where each game object is registered. However, from the .cpp, we can actually make this instance from the player client, Bullet client, so all the corresponding clients to be registered within the main client.cpp. Very quickly, I didn't realize I did not go over the dynamic object of Bullet.cpp. It's very similar to the player. However, it does not have the input process or the rotational variables. So if we look inside the right of Bullet.cpp, we can see it's very similar to the player, as it does, again, need a dirty state because the values are changing in the real time of the game. It has allocated its memory values in real time, making it a dynamic object, meaning it would need a dirty state. So you can see it's we have very similar with we're using ECRS position again, and the color and health. So if we go into bullet.h file, we can see that it's all declared inside there, all the variables that have been used, all the ECR positions and so on, and all these variables in there that we can manipulate and use. And then if we go into the Bullet server, the Bullet server is where the handle dying all originated from. So it unregistered the game object once the bullet collides, basically. So handle dying happens in the server. And because it's just in the server, this isn't due to when the collision happens. That's called in a different file. But this is just deserializing the bullet from the server after it's died. And you can see the collision with player. This is where we want that player to take damage. And then after it's hit the player, we want it to die straight away. So we set that to true, making it that the moment it collides with the player, after it's done its function, it then is deserialized. So here we have the take damage function as well for when that happens, using the dirty state as these values will be changed. Next, I want to quickly go over the server.cpp to go over the synchronization within the game. At the start of server.cpp, we have the game object registry instances with the create functions of the player from player server, Bullet server, making these static create objects. Then we have straight away in the server run, so the moment the server has started, what methods we want to call, and we want to set up the world. So if we go to that method, which is also in server.cpp, we can see that now when it starts up, we want to set up the world, and when setup world starts, we want to spawn the tire, spawn the house, spawn pickups, and we want all the static objects to be synchronized within the server. This means that no matter how many clients join or disconnect, as you can see in the do frame, we have instances for processing incoming packets and checking for disconnections. No matter how those clients impact the server, the static objects and methods that have been stated in setup world will stay apparent to the synchronization of the runtime. So whatever started at the runtime and however they change in the runtime will stay synchronized due to it being in one server rather than multiple servers per client. the clients are going to the same server, making it that they are synchronized. If we go to, for example, the handle new client, we can see that when a new client joins, we get the player ID, say spawn the player with this new local player ID, and then start the function of making that dynamic object for the player. So likewise, if we go to the spawn tire, we just have creating the static object instance within this, setting the location. And as you can see in the setup world, we already had spawn tire. So on startup, spawning the tire and all the other objects will be present, but the client player will only start when the client joins the server. To further expand upon the synchronization of the game, I wanted to quickly discuss the network manager within replication. So within the network manager.cpp, we have a process queued packet. This requires an input stream of the current packet and then passes in a pack address. Then if the packet queue is empty, the received and next packet go to the front of the queue, which we can see here, which then, if the timing instance of get time is smaller than the next packet, get received packet, and as you can see in the definition of get time if, we can see that it's a method within timing.cpp, which is in the replication, that we can see that if that is the case, then the process packet then goes back and forth until the corresponding packet is obtained with the packet address. This ensures the synchronization of the objects within the server by constantly looking for that packet. This is the approach that ensures that each packet that is queued finds its allocated packet address, meaning that when other clients join, they're getting the correct packet information to have a synchronized environment for each client to move about and experience. Now I've showed you all the aspects of code, I now wanted to show the actual in-game results. Currently I've got two clients in the background moving to show that two clients can work simultaneously, and the moment that I start up server, we will get an idea of the gameplay world. So you can see I've got them both open on the right. So if I press play on the server and I open up both of these, you can see that the NPCs are chasing me, both players are in the game. If I move, see blue is going for the other NPC while I'm dead. So if I keep moving, as you saw here, one of the pickups was taken away, so everybody's faster. But if I go to the other one moves. Once we both spawn in, I'll be able to show you how they synchronize. So see, while I was playing the other one, the other player respawned. We both collide with things. As you saw, the NPC does go for the closest one. So when I was dead, it went to the other player because it was closer. And if I go to the other one, this is also moving and simultaneous. This can hit all the different colliders as well. And as you can see, while I'm doing this on both screens, it's showing that everything is synchronized between each client and each world, whilst also showing that two clients can play at the same time. Finally, I wanted to show the unit test for the Google tests. So first, inside the Game Object Registry test analyst, I've expanded upon the setup just by adding the Game Object Registry instances for each static create pointer for each object, so house, pickup, tire, and bullet. And we can see because of that, I've replicated that within the player, like here we have the player object creation. I've now created that for each object, so the house object creation, the tire. So if we actually go into that, what I'm doing is I'm expecting the go, which will be the actual local variable of that game object instance, as we can see here. I've allocated it to be hus, which is for house. So I'm expecting that it's not going to be a null pointer. I'm not expecting that to be a null pointer. But however, I am expecting the class ID to be hus, as I've just declared it there. This is the same for each instant of this object creation. But if we scroll down, we then have a test registry world link, where you're registering the link. First, the player is done, but I've expanded by adding each of the objects. But if you actually go into this, you can see that I'm saying that another object is equal to the instance of a game object, so house, and I'm expecting that the other object will make the index of the world go up by 1, because once you add in the game object, the index list would go up by 1 because there's another object. So I've done this for each and every one to make sure that there's not a difference in the class ID having an effect on the index counter amount. This is a test to make sure it isn't the case. This links perfectly with the world test harness. So if we go into the world test harness, I've expanded upon this again by not only now having a test world add game object for just player, I've now expanded upon that, labeled it for player, and done it for each object. So test world add another game object. Inside this, I've expanded by it not only just through creating the player object, I've now got one for the tire, the house, and I'm saying that I expect to get this class ID again, but I expect that the index amount will go up to the next numerical number. So we started at 1, it goes to 2, then I added the tire, it goes to 3, added the house, it goes to 4, and so on. So I've tested that it works with a larger number, not just going from an index of 1 to 2. I'm testing to see if that will work. Then I've created individual test player object setup, adding different game object tests. This is the exact same in the game object registry, but now I'm doing it within the world test harness to ensure that the link works and each each game object pointer works throughout the test. So I'm using the game object pointer to create the house object. I'm then expecting the outcome of the new house to be null, adding the object to the world using a world instance, and then I'm getting the game object count and expecting the value to increase by just 1, because in this instance, I'm only adding 1 game object. If we open the test harness and we do the echo test, we can see at the start the game object registry test harness, the house creation, player creation, tie object creation, the world link, house link, they all are running okay, and they had no errors. Now, if we go to the bottom, where the world test harness, you can see the add object, add another object, and then you've got adding all the different objects. You can see that that index changing isn't creating a problem anywhere within the scripts.